Hello, I'm Andy Newell. I've been at Facebook for 7 years, focused on large-scale backend infrastructure challenges. The last 3 years have been devoted to helping a large effort, which is changing how we're allocating resources in our data center in order to scale. The historical way to allocate capacity at Facebook was through server pools. Large teams like ads would get a segment of the capacity in each data center to run their tens or hundreds of services. And within this service pool, the team makes their own capacity management and service placement decision. Capacity management to make sure that services don't run out of capacity, and service placement to ensure that those services can withstand the physical realities of the data center, like failures, maintenances, or shared resources. What this looks like from a contract perspective is that data centers have some contracts they provide around some assumptions about how things fail and maintenances that occur. And through the pool operations, there are these higher level contracts that service owners build against. And these service contracts will differ pool to pool depending on how that team implemented those pool operations for capacity management and service placement. This has lots of problems. One, there's lots of duplicated effort. Many teams are doing very similar work to perform capacity management and service placement. Another is that there are inconsistent contracts for service owners, depending on which pool you're in. So a service that's built really well for one pool might have to be changed or won't translate well to other pools. And then there's capacity fragmentation of the data center resources. Here's a timeline over the past 5 years of how many server pools Facebook has had. Starting in 2017 and 2018, we saw this alarming trend of roughly 3 times the number of server pools came up. And we're really feeling this pain of all these teams duplicating effort. And that's when planning began to correct the situation. And recently, we've rolled out many big changes and push people towards a shared pool. And we're actually starting to reduce the number of server pools now, and we're headed towards one single pool. This is what this will look like from a contracts perspective. You have the same data center operations contract, and now you have one set of service contracts that all services can build against, and it's a very stable set that will be long living. You get very clear expectations for all services. We get fungible capacity. All the services are now sharing the same capacity, and we can consolidate all these pool operations into one effort. And that's actually where RAS lives. We're able to unlock this ability to perform these pool operations at scale, where instead of there just being tens or hundreds of services, we have thousands of services that need to share an entire data center's worth of capacity. In this talk, we're focused on guaranteed regional capacity allocation. And a region is a set of data centers that are physically close to each other. There are other layers of the Facebook stack that handle global allocation across many regions, and then elastic offerings that utilize compute when it's being unused. But that's not what we're talking about here. This is about allocating critical services within a region, and there are thousands of such services that have to be running for the basic functionality of Facebook and our infrastructure to operate. There's a very diverse set of services. So there are challenges in the different ways that they request capacity. Some services will request, say, 10 servers of compute. Others will be specific and say, I want this many of each CPU generation that exists in the region. And others will have a more fungible approach where they say they know how much QPS or how much throughput every server type can provide, and state some overall peak throughput that they need to supply with their service. And then we can provide any mix of capacity that matches that. Another challenge is that this is not static. The amount of capacity every service needs changes over time as new services are created, as they upscale, as products become more popular or less popular. So there are hundreds of modify, create, and delete operations to how much capacity is needed each day. One of the big challenges is how to supply all these diverse set of services, given some of the challenges in supply of our physical data centers. So One challenge is the scale. A region consists of multiple data centers and overall hundreds of thousands of servers across 20 types of servers based on breakdowns of CPU generation, memory, GPU, ASICs, and it's not a static layout. Every server has a several-year lifetime, and when that lifetime's over, we have to decommission that server, and we'll be buying and purchasing and putting in new hardware of the latest generation into our data centers. So every year, at least 10% of servers are being decommissioned, and at least 10% of new servers are coming into the data center. Then there are many types of events that happen. One are random failures. Servers can fail randomly for many reasons. Then there are correlated failures. We actually identify these hardware components in the data center that can bring down the most servers. And these are hardware components that we don't build redundancy for. So that long term, we expect there to be some of these large failures in the data in a region, and we want to still operate that region during one of these failures. Currently, it's on the order of about 10,000 servers, and it's based on some power device hardware. So when one of these fails, every service still needs capacity. Additionally, that same hardware needs maintenance. So one of those failure domains may go into maintenance as well. And every service still needs capacity to run. To handle all these challenges and operate this shared pool, we need a really strong pool operations that can handle this from a capacity management and service placement perspective. And what we came up with was this abstraction of reservations. And these are provided by RAS, which is called the Resource Allowance System. What service owners will do is make their request for capacity first. And this is of a form like I need 100 compute servers or 40 servers with 128 gigabytes of memory. And the RAS system will take the collection of all reservation requests in the region, and then the entirety of all supply that we can fulfill those requests with, and perform a solve. And solve for many things from capacity management to service placement, various placement goals that help us offer the best service expectations to service owners. With this approach, capacity management becomes straightforward as it's very clear that every service has the capacity they require, as it's specifically marked in the data center by RAS. Additionally, we can give a lot of service placement guarantees, given that we are consolidating all of this allocation to one single solver that gets to consume the entire set of reservation requests and the entire supply and make one assignment. This is the architecture of how we were able to do this, starting with what existed before. So service owners would just create jobs, and when they started those jobs, containers would be placed on servers. So there's a container management system at Facebook, it's called Twine. And then there's a set of servers that exist in the region, and this is stored in a database called Resource Broker. On top of that, we built reservations in that database. So every server is tied to some reservation. And then we added this other level of allocation. So this is a two-level allocation system where first, the service owner will request the capacity they need. And then once they get that capacity, they will start their job and run and do all the container management they need. So the capacity request will come to a database in RAS, and RAS will have the latest set of all requests that have to be fulfilled in the region. It will get the state from Resource Broker of all the servers and what their current assignment to reservations are. And it will output a solve result back to Resource Broker as a target reservation. We actually allow RAS to reassign servers and actually take servers away from services and provide them to other services in order to rebalance the pool and achieve placement goals despite all the dynamics of demand and supply changing over time. And then a new service had to be created that safely transitions servers between these reservation boundaries. So whenever a target reservation doesn't match a current reservation, this movement service will ensure that it's safe to remove from the source the source reservation by draining that server safely and then transition it to the target reservation. So this architecture allows us the single point where we can optimize many placement goals at once and offer these nice contracts and guarantees to services when they get capacity through RAS. In this talk, I'm going to talk about the first three listed here, but we actually do solve for all of these in production today. If you want to know more about the others, there's an associated blog post that goes into more detail on each one. So we had a design choice to make in how we do this solving. We actually ended up with mixed integer programming as a solver due to the design requirements of we need to balance many policies against each other given the same assignment. And the modeling of mixed integer programming allows us to do this very formally. The quality of the solution impacts highly how efficient we use the resources in the data center. And we're given this computational slack of 1 hour, a 1 hour SLO to do this solving with. And that allows us to use a heavy tool like mixed integer programming. The formulation of this problem is built on assignment variables. So what we do is for every unit of supply that we have and every unit of demand, so servers and reservations, we make some variable, and the value of that variable reflects how many servers we're assigning of that supply to that particular demand. And then we use off the shelf, and then we can build all these placement goals on top of that with linear constraints and objectives. Then we use off the shelf commercial solver and let that reason about the combinatoric packing difficulties that exist with such a problem. We did have to do one major modeling change to ensure that we can scale, and that was to leverage symmetry. The very straightforward way to do this implementation would be to have every individual server be a unit of supply and every reservation demand. But that Cartesian product would be about 1 billion assignment variables, and that's not tractable to solve in 1 hour. So what we do is we group servers by what's logically equivalent according to our modeling, and create a mixed integer program with these assignment variables that reflect many servers. And that actually gets us down to the range of 1 to 10 million assignment variables, and that's actually tractable within the 1 hour SLO. So now let's start talking about those placement policies. So the first one is capacity requirements. This is the bare minimum that RAS must do. It must give every reservation the capacity they require. And there are all those different forms of capacity specification. And we can actually capture these through this basic formulation of taking the linear combination of some assignment variables that reflect how much capacity you assign to a particular generation of server in the data center, and take a linear combination of those, and through one or more of these constraints and adjusting those coefficients, you can actually capture basic server counts, server counts per generation, or that more fungible relative unit approach where they express their desire of how much throughput they need. This is what it looks like in production. So in this Venn diagram, you can see that there are many services that will request for any compute server, and they would end up in the middle of this Venn diagram because they can take any of the 3 generations of general compute server that we have in the region today. And on the right shows the supply of each generation. So this is actually one case where it's really important that we have this single solver that has a full view of the region and can solve for everything at once. Because if you were to fulfill that middle of the Venn diagram with a lot of the generation 1 or generation 3 servers, you will actually deplete those types of servers. And then other reservations desiring just those servers could not be allocated. So RAS ensures that we meet all of these requests at once. Then moving on to the other 2 placement policies that I wanted to cover. They're actually both related to spreading requirements. So one is about failure domain buffer, where we want to spread reservations across those failure domains and ensure that they have sufficient capacity to survive a failure. And then that doubles as both what happens in a failure scenario and when we have to do a maintenance on those large failure domain. And then the other is to help with avoiding overloading rack switches. So that is to spread reservations across racks. So a reservation that could be very costly in terms of network, it's spread across many racks and doesn't overload one specific rack switch. So here's a high-level view of what those formulations look like. The first two are related to failure domain spread. So we actually take the capacity requirements that I showed before, and we duplicate them for every single failure domain, and we ask the modeling, let's make sure they have their requested amount of capacity despite failure domain 1 being down. And then we say the same thing for failure domain 2 being down, and we find some assignment that ensures that they have their capacity despite each individual failure domain going down. So we meet all those constraints at once. And then on the rack side, we ensure that the amount that we assign per rack for a reservation is under some desired amount that we want for that particular that reservation. And then we add some variable penalty term, and we try to minimize that penalty. So if you're under the desired amounts, you won't incur a penalty, but if you do go over, we pay some penalty in the objective, and we weigh this penalty with other goals that RAS has. So now I'll show an example of failure domain spread in production. Here's a heat map of capacity supply. The columns are failure domains, and the rows are server types. And the darkness of the cell reflects that server type and failure domain combination there are. You can see that it's not very even, so you can't just easily spread all services exactly evenly across these failure domains. And there's some reasons to this. Here's an example of we shifted from one CPU generation to a new one for our compute server. And then here's an example where we actually discontinued a type of server, and we're not going to add them in future turnups of new capacity. So this is what RAS does in terms of allocation in the pool. So here's an example with, again, every column is failure domain, and here every row is a reservation. Here are the top 30 reservations. And the darkness of the cell is how many servers we allocated for that failure domain reservation pair. And what we want is the colors to be very even across the rows. And we get that mostly with RAS. The perfect with 36 failure domains would be to spread services perfectly evenly, and we'd have 2.8% extra servers allocated to this extra failure domain buffer. But in actuality, we get 4.2%. And actually, we're solving nearly optimally given the hardware spread that we're given with achieving that 4.2% overhead. So we need better hardware spread to do even better in terms of that efficiency. Some ways you can see the inefficiencies of hardware spread here. These reservations request a specific server type, and that hardware for that server type only exists in certain failure domains. And here, this is actually a networking constraint. There are some reservations that do so much networking with other services, and we have limitations at the building level for how much bandwidth we can use. So this reservation is co-located in the same, needs to be co-located in the same building as another service. And it can only use, thus it can only spread across the failure domains in that building. Now moving on to a view of rack spread. This is a probability distribution where I'm showing the percentage of all reservations. So the y-axis is percent of reservations, and the x-axis is what bucket it falls into in terms of its rack spread. Where rack spread here is a measure of the percent of that reservation that's in the largest rack for that reservation. For our service contract, we're actually targeting 2%. That typically does well in terms of making sure that services aren't highly correlated with, highly packed into certain racks. And we actually achieve 90% of the reservations hit this 2% or less. And there's a small set that are, and then actually many more are very close to that 2%, but then there's these outliers. And this is actually due to the hardware spread as well. So these are services that request a very specific hardware, and it's actually not in very many racks, so we can't get that really widespread across the racks. And RAS has to do these trade-offs all the time. So in this case, it's trading off and saying it needs to do capacity fulfillment and not fully obey the rack spread goal. So in conclusion, we've rolled out this new 2-level allocation for the shared pool that's actually provided these really strong pool operations that have allowed us to start moving all of the services towards this shared pool. And today we're at 80% of all Facebook capacity is running in the shared pool. And we're headed towards 100%. I think on the way, we have to handle some challenges of storage services that have extra service requirements. So we just finished the production rollout 1 year ago, where we launched RAS in the production shared pool for Facebook, but we have a lot more that's coming up. We just got the architecture there, and we can do a lot more in terms of placement optimization. We can do modeling of network and power placement. We want to be able to stack and run many reservations on the same machine and share resources even more, and optimize for network flows. Thank you all for listening to my talk. I look forward to any questions you may have.